This is Timothy Wood with Citadel Civil Engineering. This is CIVL202 Statics, and in this lecture we're going to be discussing applied moments, force couples, or moment couples, which are actually all different words for exactly the same phenomenon that we're going to be looking at. Just as a reminder, we are talking about force systems, and we're going to be looking at rotation of rigid bodies. So just as a quick thing in context, we've talked about forces when we were doing particle work, so we could have a point and we could push on it or pull on it with our forces. Now, if we were to allow things to move, this is statics, nothing is moving, but if we were to allow things to move, that application of a force in general is going to want to cause translation. Okay, so we push on something and it slides, or we pull on it and we lift it, and so it's causing translation. And for particles, that's the only type of meaningful motion we can have. If we think about spinning a mathematical point, that doesn't have a meaning. Forces will continue to cause translation for rigid bodies. However, now that we're doing rigid body, we can also think about the rigid bodies rotating. So if I have some rigid body, it can spin. And we remember from our conversation earlier that moments apply rotation. So they have a tendency to cause rotation. So they tend to cause rotation. What's unique about an applied moment or a moment couple is that not only do they cause rotation, this particular concept is going to cause no translation. So as opposed to our general moment calculation, in which we might have an isolated force that's generating both rotation about a particular point and causing the body to translate some of the forces, an applied moment's only going to cause rotation. So if we think about, okay, I've got a thing and I want to rotate it. What would be a natural way to rotate it? Well, maybe a natural way to rotate it is with a screwdriver. So we take a screwdriver, we put it on the screw, and we spin it, and we cause rotation. And if that were the case, we just draw a little curlicue like we do for our sign convention. However, let's think about another common example. Let's take a look at this. This is my bad diagram of a steering wheel. Think of a big bus driver steering wheel. And if we think about turning a car, hopefully everybody's had the experience of driving a car or turning a steering wheel. When you turn the steering wheel, we could just grab the center of the steering wheel and we could twist it, or we could even get a screwdriver and go straight to the middle and twist it and apply a moment that way. It would cause rotation. It's bad news when our steering wheels translate. We don't actually want them to translate up and down, left and right, unless maybe we're adjusting them when we get in the car. But in general, when we're trying to turn, we don't want translation. We just want rotation of that steering wheel. And so we could twist it in the middle. And if we were to do that, we'd draw a picture that looks something like this. But that's probably not how you steer. Instead, you're going to put your hands at 9 and 3, not 10 and 2. 10 and 2 is old school, but now airbags, you'd punch the ceiling. So 9 and 3. And you would apply a force in one direction, up, and a force in the other direction, down, that would tend to cause that rotation. And it would be equivalent to the same rotation, the same applied moment needed to twist the column directly. So let's look at two forces. Let's look at a force couple or a moment couple rather than a twist that would generate a similar type of moment. So here's my two forces. Here's one force, I'm going to call it negative F. Here's another force, positive F. And we'll notice that with these two forces, so we have two forces. This is our definition of an applied moment or a force couple or a moment couple. We call it a moment couple or a force couple because there's a couple of forces there. Two forces that are equal in magnitude, F, equal magnitude. They are opposite in direction. We can put our sign convention on here someplace. Ooh, I'll do a rotated axis. Like so. Okay, so one's pointing in the positive x direction, the other's pointing in the negative x direction. By the way, if we had two forces equal in magnitude applied to the same point, that would actually be Newton's third law, action and reaction, right? But in this case, the new thing is that we have a separation. Separated by a perpendicular distance. Okay, and we can sketch that perpendicular distance like so. So it's separated by a perpendicular distance. So we might ask ourselves, okay, there's a couple of forces there. What can I find out about the forces? Well, one of the things I might want to find out is the resultant force. How much is the push or pull? And we know that the resultant force is going to be equal to the sum of the forces. We did this in our particles. We think about all the dogs pulling on the dog walker, adding those all up. And if we did that, we'd add these things in here and we would have our forces like so. And if we add two forces that are equal in magnitude but opposite direction, we're going to find that we have 0. So part of the reason we have no translation going on in this case is because we have no net force. Okay. The next question I might ask is, what's the resultant moment? Yeah, what kind of twist is happening here? Okay, so just for what it's worth, this is what we're looking at, right? We're thinking about how we'd actually drive a steering wheel. With that in mind, I'm going to close this out so that you can hopefully see the board a little better. Here's my resultant moment. But remember, when we calculate a resultant moment, r cross f is going to be our thing, and we need to identify our point of rotation. And we can pick any point we want, although we know that in the general case, what point we pick matters quite a bit, right? Because the farther the lever arm, the more moment we get. So if we pick a point far away from our force, we're going to get more moment. But let's see if that's the case here. So what I've got here is the resultant moment. Let's calculate the resultant moment about A. So I need to identify my forces and their perpendicular distances. If I start with the positive force down here, and I look for the perpendicular distance from A, so I'd have, this is my position vector, R. R is, oh, it's D long. Look at that. Okay, so cool. So I'm going to have D times the force, the magnitude of the force. That's not the derivative of the force. That's this distance times force. Maybe this is helpful. Put it like that. And we could use my right-hand rule. So R, F, thumb out. That's positive. Or I can start at A, R cross F, positive, out of the board. Or I can think of it causing counterclockwise rotation. That's going to also be positive. So all's good there. Now, when I look at the force, this negative force, what's its perpendicular distance relative to A? This is something important for us to see. It's pushing on A directly, right? What happens when a force pushes on a point? Well, it's going to tend to cause translation, but there's no perpendicular distance to cause rotation. So our perpendicular distance for this negative force about A is actually 0. So we're going to have 0 times that force there. Okay. And because I've got the arrow over the top, I'll need to indicate my sign convention. And so I draw my counterclockwise curl in the positive direction. So if I add these up, I find out that the resultant moment about point A is simply going to be the distance D times the force F. The magnitude of the one of the forces separate by the perpendicular distance separating them. That's interesting. Let's look at another point. Let's look at point C. I think this is going to be pretty similar, but let's go ahead and check it out. The moment about point C. Okay, so if I start with this force F here, what's the perpendicular distance from point C for that force F? Well, hopefully you're seeing that it's 0, right? Because it's pushing directly on the force. So we're going to have 0 times the force F. Our perpendicular distance from C up to the line of action for that negative force is D again. That's cool. So D times our F, that's our R cross F. My right-hand rule, so R, F, thumb out of the board in the negative direction. So that's positive. Or I can do R cross F, thumb out of the board, or counterclockwise rotation about C. Be positive. Need my sign on there. Well, again, just like we said here, that 0 times F goes to 0. We've got the same thing again here. So our moment is the same. Very cool. All right, let's check out moment at B. This one's got to be more interesting, right? There's some real mirroring going on here between A and C. Let's look at our resultant moment about point B. Add up all of our R cross Fs. All right, So if I start with my positive force, my distance here, if B's in the middle, is going to be D over 2. Real perpendicular distance there. So D divided by 2 times the force. We'll do our R cross F. So R, F, boop, R, F. Coming to the board, or R cross F, or counterclockwise rotation. So that's positive. And then when I go from this to the negative force, its perpendicular distance is also D over 2. So perpendicular distance times the magnitude of the force, I'm going to have D over 2 times the force. R cross F is positive. R cross F, positive. Counterclockwise rotation. So I end up being able to add these together like so. And when I do that, my F terms I can collect. I have D over 2 plus D over 2. Well, 1/2 times D plus 1/2 times D, that's just D times F. And so we get the same answer here. And so the cool thing about this is, if we notice what's going on here, is that no matter where we sum our moments about, an applied moment or a force couple or a moment couple, it's all the same idea, is going to have one moment no matter where we sum our moments about. And this is really, really exciting to us, because what this means is that we can call this applied moment a free vector. Okay, a free vector. And we'll talk about a little demonstration that you could maybe find a friend and do together. But the idea is that an applied moment, or a moment couple, or a force couple, again, all the same ideas, an applied moment is going to have the same tendency to cause rotation. So same moment about any point. Okay, so the idea is that then I can take this an applied moment and I can apply it anywhere I want and get the same tendency to cause rotation. So if I'm just applying twist, I can put it wherever I want and I'll get that same tendency to cause rotation. So it turns out, if I was going back to my steering wheel example and I didn't want to do the big steering wheel thing here, I could actually take my screwdriver, and rather than going to the center, I could go out to an outside handle and twist, and it would generally cause this, it would cause the same rotation. Now the tricky thing for us to do is applying moment that doesn't also have a net force. So that can be tricky. The idea is that we can move this, so we can relocate the force. So your author uses the term move. I'll use the word model at, we're going to move or model our moment, our applied moment, to any point without changing the external reactions. Okay, so this is starting to get us in the direction of being able to do equations of equilibrium. Okay, so here's my question for you. We talked about our applied moments. We showed what they are: two forces equal in magnitude, opposite directions, separated by a perpendicular distance. Their magnitude is always going to be one of the forces times the distance between the two, and it can be moved anywhere we want. So my question for you to think about is, when you decide to drive one-handed, you're applying one force with your hand. Where's the other force coming from? Okay, so I want you to have an answer to that when we come back together in class. Another way to ask the question is, if I take a wrench and I apply that wrench to a nut, usually I just apply the force at one end. So where's the other force coming from? The two forces equal in magnitude, opposite direction, separated by a perpendicular distance, that's tending to cause that rotation. I look forward to talking to you in class, and I'll see you then.